Consider the Veil Nebula, a cloud of heated dust and gas located about 2,400 light years from Earth, where a light year is the distance light travels in 1 year, or approximately 9.5 trillion kilometers. The unique structure is the ongoing result of a supernova that occurred 8,000 years ago. The shock wave from the explosion is colliding with a cloud of gas and dust, creating rope-like filaments and a sheet-like appearance. Scientists compare newer images, such as this 2015 image from the Digitized Sky Survey, with detailed images taken by the Hubble Space Telescope in 1997 in order to understand the nebula expansion and other properties of astronomical objects. The forces that cause the supernova remnant to act as it does are the same forces we contend with here on Earth, whether we are planning to send a rocket into space or simply heating a new home. Although the scale is much different, the interaction of gases in the Veil Nebula resembles those on Earth, and the vibrant color combinations are created by the familiar glows of hydrogen, sulfur, oxygen, and similar elements that make up everything we know. Tonight, take a moment to look up at the stars. The forces out there are the same as the ones here on Earth. Through a study of physics, you may gain a greater understanding of the interconnectedness of everything we can see and know in this universe. Okay, so my name's Jason Harlow. This is the pre-class video 1 for Physics 131. And what I was doing just now is I was reading from a book called College Physics, published by OpenStax. It's the 2nd edition. I happen to have a paper copy, which I ordered online. But there's also an online version, and you can also download the PDF. It's a totally free textbook, so that's a good thing. So you can type College Physics OpenStax, OpenStax, all in one word there. Google it up. There it is, College Physics 2E. This takes you to this web page, and the whole book, like I say, is available. There's a table of contents. You can click on View Online, and unfortunately it asks you to give, so don't do that. Just go to your book. And look at that. That's right where we just were. It also encourages you to log in. Once I've logged in, it shows my little initials up there, and at this point I can actually do things like highlight, add little notes and things. This is so cool. And then when I come back and read that later, I can see my own little notes. So that's a cool thing. Another way to view this book, so they say recommended view online. I actually recommend you just download a PDF. So what that means is that it actually stores the whole entire book on your hard drive of your computer so that you can open it up on the subway or anywhere without any internet access and see the book, and there's no waiting or anything. And you can print little parts of it as you wish. So I'm just going to click the download button. It saves this PDF. And now when I open up a folder and click on wherever I put it, there it is. It's called PDF, College Physics something PDF. And then I can open it with Adobe or whatever PDF viewer I have. And there the whole thing is. Now it's a 1,697 page PDF, so it is a little bit long. But if you know that today's reading starts on page 23, you can just click on 23 and start from there. And I think it's nice to just send it to my printer if I want to, actually read a piece of paper, or I can read it on the screen, and you don't need the internet. So that's how I'd recommend it. So this is actually how we're going to look at for the rest of this video. Basic idea. All we're doing, starting on page 23 here, chapter 1, Introduction to Physics. We talked a little bit about the Veil Nebula already. It talks a little bit about the history of technological periods. Stone Age, Bronze Age, Iron Age were marked by our knowledge of physical properties of certain materials. This knowledge all stems from physics, whether it's the way a rock would flake when constructing a spear point, the effect of integrating carbon with iron in southern Indian and Sri Lankan furnaces to create the earliest high-quality steel, or the proper way to perfectly ground polished pieces of glass to to create optical instruments. So, and then the information age is based on little MOSFETs, which were invented by Muhammad Atala and Dahan Kang, metal oxide semiconductor and field effect transistors. And okay, so I think the thing to know about these pre-class videos is that they are not intended to replace the reading. You have to do the reading. You may also watch these pre-class videos, but they're mostly meant really to kind of motivate the reading and to give you a basic overview. They're not meant to replace the reading, I'm afraid. So you can skip the videos, but you can't skip the reading. You gotta. The course is based on the reading. So yeah, I mean, a lot of chapter 1 is giving you some history and some perspective and motivation on physics itself. So I'll just sort of scroll past some of this. There's a scientific method, really important to understand. Difference between a model, a theory, and a law. I would look at those since we're going to be using those a lot. I hate this image actually of the electrons going around because this is like the canonical kind of science-y image, but in fact electrons don't do this. Any chemist who looks at this will be aghast, okay, because electrons exist in stationary states and probability density clouds. They don't go in tiny little circles with little strings around them like that. Okay, I'm just going to keep on scrolling along. Again, lots of history here. Some stuff about reminding you that what we're going to be learning in this course is what's called Newtonian mechanics, which has been around for quite some time now. But in the 20th century, there was something developed called modern physics, which includes two revolutionary theories, relativity. Einstein's relativity, developed in 1905, and later including gravity in 1915, and quantum mechanics, which was developed in the 1930s. These theories are the real physics theories that deal with everything, but you don't really need them. Newtonian mechanics is a good approximation to relativity and quantum mechanics as long as things are kind of slow, like less than 1% the speed of light, and kind of big, like you can see them in, without a microscope. So that's good to know. And then section 1.2, we're getting into physical quantities and units. So again, I'll scroll through this kind of quickly, but there are things called units. This is somebody puzzling over what the unit of a cable is. It's a unit of length, I guess, but if you don't know what it is, then the map doesn't mean much to you. So there are standard units we use in science: meter, kilogram, second. Amperes is more of a physics 132 concept when you'll be studying electricity and magnetism. There's some basic stuff about how the second and meter and kilogram were originally developed. Prefixes, hopefully you should know a little bit about this from high school, but kilo is 1,000, giga is mega is 1,000,000, giga is 1,000,000,000. That's for bigger things. If you're doing smaller things, then milli is 1,000th, micro is 1,000,000th, and nano is 1,000,000,000th. Okay. We're going to do unit conversions in this class. So if you wanted to convert 80 meters to kilometers, then you can actually multiply by a conversion factor which you know to be 1. So you know that 1,000 meters is the same as 1 kilometer. That's what the kilo stands for. So 1 kilometer divided by 1,000 meters, that's 1. So if you multiply this fraction times 80 meters, then the meters in the bottom of the fraction cancels the meters in 80. And so all that's going to be left is kilometers. And then you just take the numbers that you see here and multiply or divide them. If it's on the bottom, you divide. So you have to multiply 80 times 1 and then divide by 1,000. So 80 times 1 divided by 1,000. On your calculator, you get 0.080. And that's how many kilometers 80 meters is. So it's a good trick. We'll be doing some practice with that. So there's an example you see here on page 40. You should definitely work through that. Non-standard units, you might hear about these things like pounds, for example. Pounds can be converted to a unit of force, actually. We're going to be using newtons more. And then that's the end of today's reading today. So I'll see you next time. Bye for now.